Okay, good day to all of you attending. My name is Ramon Hansen, and I was invited to give a short introduction or a lecture about SAR interferometry. And yeah, so the point is it's an online lecture, so I don't see who is participating, and unfortunately I also cannot interact with you. I just heard half a minute ago that I cannot ask a question or ask you to raise your hand or so. So that changes things a little bit, but it will just mean that I'm talking into the blind, and I will just assume that somebody's out there listening to me. Okay, so welcome. I was asked to give a talk about SAR interferometry, and actually there are many talks about SAR interferometry and SAR already available online. What I put on this first slide is a QR code of a long lecture that I gave going over all the principles of INSAR for an ESA course a couple of years ago, and basically the basic things didn't change, so the equations are still there. So when I was preparing for this lecture, I thought that it would be valuable to give you a bit more or a bit different perspective than what is already out there. So I decided to do that. So it will be maybe at a little bit higher abstraction level, but I think perhaps even more relevant. What I was told is that there were a couple of hundred participants to this lecture. And I guess, I don't know the background of everybody who's listening and looking, but I guess some of you are starting to work with INSAR or planning to or are working with it and would like to know more about it in terms of the interpretation. So this is what I'm going to talk about. Many of these kind of talks start with highlighting how beautiful the technology is and what we can do with it. And actually, it is a fantastic technology, and I'm working on it for a couple of decades now, but I'm amazed with what we get out of it. But I choose to start with a different approach. And so basically my main message to start with is INSAR doesn't work. And I think this is a better way of starting the talk than showing you all the great results that are out there. So this is a bit provocative, I understand that, and we can make it a little bit more nuanced by changing it to, okay, maybe it works, but there are exceptions. Maybe some of you have already encountered that you tried it at some location or some situation, and it didn't work as you liked, or the results were not so nice, or you had questions about it. And you can also turn this one around. So basically, you could say it doesn't work unless we can make some assumptions. And basically, the first part of my lecture, so I have 2 hours now, I will probably divide that into 3 parts. The first part will be on this perspective. So let's start where we are now with the INSAR state of the art and see, okay, what is out there now? Well, first of all, everybody knows there are many, many missions out there, more to come. Very interesting, the upcoming NISAR mission from ISRO and NASA together, L-band, S-band, that would be very, very interesting. But there are many, many other sensors out there. The data are available, the data are accessible. In many cases, you can download them easily, so you can basically get to work immediately. The second thing that is there is the methodology. There is software out there, and you can download that. You can basically start doing your own data processing if you like. Different methodologies, point scatterers, distributed scatterers, different processing schemes. And also the tools that we have are available and accessible, and well, that's all great. Another development that is happening right now, what you can see, is what people call analysis-ready products. And the philosophy behind analysis-ready products is that the end users of INSAR data are maybe not so interested in all the nitty-gritty details of how to get there, but they just want to work with it. And that is called an analysis-ready product. And there are several examples of that. I show you here 5 of them. These are basically nationwide or even region-wide products. So for Norway, for the Netherlands and Belgium, for the UK, for Denmark, for the whole of Europe. So there are all these kind of tools available, and I'm sure you can find them, and you have played around with it. If you didn't, go to one of those sites, and there's a browser you can zoom in and zoom out and click on points and see time series. So basically, that's all out there. So a lot of analysis-ready products. So you could argue, okay, so this is all out there, so we're done. Right. In that case, there would also no need for you to follow this course, because why would you invest in becoming an expert in this field if it's already out there? Right. And this is basically the question mark. So are we done? Is this really technology that is out there? We can deploy it. Well, my vision on this is that we have to talk about information products from INSAR, and information products, in my definition, could be either a map or an online portal, or maybe a database that you can download with numbers in it, or graphs or papers or reports. And there could be many different information products. And these portals that I just showed are one of them. So the question is, are we happy with this? Well, to explore that, I would like to give you one anecdotal example, and I would like to, the idea was that I would get a bit of input back from you, but unfortunately I cannot see any response. So the moderators of this course probably can, but I'm not sure if they can pass it on to me. So I'm going to ask you a couple of questions, and I'm going to ask you to answer it for yourself, and then we'll see where we get. So the example is as follows. So this is one particular product, but I could have chosen any other. This is the European Ground Motion Service with data over the city of Porto in Portugal. And I was there a couple of years ago for a lecture, and my house was somewhere. So I thought, okay, let's have a look at the location where I was staying. And basically, Porto is very famous because of this bridge. I'm sure if you can see my mouse, I hope you can. But this is one of the bridges of Porto, Porto Dom Luís, the Eiffel Tower-like bridge. There's another bridge over here. And basically, we could have a look at, we could ask ourselves, maybe can we monitor those bridges or so with INSAR? Now, if you then switch on the data, and there are many different levels of data that you can choose from, but typically you get, with these kind of products, maps like this. So these are colored dots over a background photograph. And what you see is, well, this whole, all these beautiful colors of dots, and they represent motion, in this case, average velocities over a certain period of time, probably a couple of years here in this case. And what you see is very interesting, because some of the bridges, for example, this one, this on the right-hand side, unfortunately, we don't have any points. And then we have points on the bridge that I was talking about, Pont Dom Luís, in the middle, not so many, but at the side. And very interesting is that we have this kind of feature here on the left, where actually we find points, but there is no bridge. Right, so I tried to make a joke, calling this Pont Dom Transparente, that it would be a transparent bridge. But well, okay, there are data there, there's no bridge. Now, I have a couple of questions that I would like to ask you, and I'm going to ask them, and then I'm going to wait for a couple of seconds to think about an answer for yourself. Okay, so the first thing is, so this is an anecdotal example, right? I just picked something. And okay, we have data over a bridge that doesn't exist. So the question that I have, does this mean that the product that we're looking at, this INSAR information product, is bad? Right? Please think for it for a minute. Is it bad? Okay, well, I can give you my answer. The answer is no. I don't think the product is bad. Second question, I will review the questions a little bit later. But the second question is, does this mean that the product is suboptimal? Right? That is it's not as worse as bad, but it is also not good. Suboptimal. Would you say it's suboptimal? Well, for me, the answer would definitely be yes. Right? We have data on a bridge that doesn't exist. There are other, on the right-hand side, there is a bridge where we don't have data. So probably it could be better, at least suboptimal. Then we get to more interesting questions, and that is actually, does this mean that this product is useful? Right? Okay, think about it for a second. Can we do something with it? Okay, my answer would be, maybe it is, maybe it isn't, I don't know. Okay, fourth question. So if you would agree with me that the product is suboptimal, then the question is, why is it? Why do we say that? Why do we call it suboptimal? I put an exclamation mark behind the yes over here, so I'm very confident that I think it's suboptimal. But if I would need to articulate why, and this is actually the main point of this first part of my lecture that is coming up now. So again, I give you a couple of seconds to think, why is it suboptimal? Okay, so my answer here is because this product is application agnostic, as we call it, or AA. Now, what does that mean in my terminology? Well, it means that this product was made without knowing what the application of the product would be, right? Basically, we're just making an INSAR product because we can. We have the computers and we have software and we can make it, and we think it would be nice for people to share. But it was definitely not made to monitor this particular bridge, right? Now, you see many presentations about products like this, and not only the European one, but also the Dutch one, where we would have an example like this bridge, and we would analyze the dots and see, hey, there's thermal expansion, so see what a beautiful product this is. But you would never see a product on the right bridge, where we coincidentally don't have any points over here. And I don't blame anybody for this, because it is just a consequence of making an application agnostic product. Agnostic means that we cannot know what the application would be. Okay, I'm getting back to that in a minute. So next question, would it be possible to make something better to monitor, for example, this bridge or the other bridge? Well, my answer here would definitely be yes. We could probably make something better. And what would it take to make something better or optimal to monitor this particular bridge? That means, for me, the answer to this question is that we need to be application aware. And this is the key point, right? So with the technology that we're discussing today, INSAR, we can basically make many, many products. And if we don't know why, for which purpose we're using it, or who is using it, then it is application agnostic. If we're application aware, then we can do something specific. Okay, so coming back to the question, are we happy with all these INSAR information products that we have? Well, actually, yes and no. So I distinguish two types of products: AA products, which are application agnostic, and AAA products, which are application aware. So I know what I'm going to do. I know beforehand what my goal was when I created the product. And aligned. And aligned means that because I know the goal, I can tune my processing scheme, my parameter estimation in such a way that I get the results that I want. Now, why am I addressing this? Well, that is actually because this is not special at all, right? I'm a geodesist, and so if we look at traditional geodetic techniques like leveling, for example, we would never dream about just going somewhere on the street and doing some leveling and hoping that maybe somebody would find it interesting or would work with these data. That would never happen. We would always first have a question, and then we think, okay, what do we need to do? Why do we need to do it? Who's interested in it? What is the goal? So we're always application aware when we do these kind of surveys. If we put a GPS antenna somewhere, we always know that there's always a reason why we do that, right? And the funny thing with INSAR and this kind of technology is that the data are acquired anyway, and we're just opportunistically trying to figure out whether we can do something with it. So distinguishing these two categories, application agnostic and application aware and aligned, AA and AAA, allows us to to categorize and to get closer to a good quality description of these products. So what is the implicit premise underlying this analysis ready data philosophy? So basically it's a one size fits all approach, right? So these kind of products, they say we process something and that's it. And there is underlying it is an implicit claim of optimality. Usually if you go to these kind of sites and these kind of products, so including the ones in the Netherlands that we're making ourselves, it's always trying to describe what we can do with it. So there's an implicit claim that it is suitable for that. And that is a problem, because if you have such high expectations and you're interested into the rightmost bridge in Porto, for example, you would definitely be disappointed, because you have seen beautiful presentations from other bridges where beautiful things came out, and now here for the bridge that you're interested in, you cannot see it. And if you're disappointed, you also will not use the technology for the next time if you are interested in it. So we can avoid that disappointment and disengagement if we categorize these two products. So I have no problems with the generic AA products because they're application agnostic, and I don't have therefore any expectation that they would be optimal for my application, because I know that they were not made without knowing what the application is. However, if it's a AAA product, where you first need to know the application and then design the optimal measurement strategy, you choose for the sensor, for your threshold for allowing points or not, how do you estimate parameters, then it is something that we can talk about and we can reach optimality. So if you have a AAA approach, you know what you want to do before you start processing. It will lead to improved estimates of displacements, and that can help for day-to-day monitoring and risk assessment. So this is basically my first statement on INSAR at a high abstraction level. The second one is what is basically I call it, it's a little bit fancy, but the tripartite nature of causality. And what I mean with that is that if I would ask any student or institute or university or company to process leveling data acquired over a particular area, so people went out, did some leveling. I hope everybody understands what leveling is. So going into the field with an instrument, doing a measurement, would it matter a lot which party I would ask to do it? Well, I think it would matter a bit, but actually not so much, right? As long as you know what you're doing, the strategies are clear, you know what you're measuring, I think there would be not so much. There will be some difference, definitely, but it will not be so dramatic different. However, if I would ask a student, an institute, a university, a company to provide an INSAR result over a particular area, would it matter which party I would ask for it to do it? The answer would be definitely yes. I would definitely get. We did several experiments on this, and this is also not so strange, because there are basically three aspects that play a role here. These are the data, the method, and the operator. So if I would, this is what this tripartite nature is. So if I would change any of those three components and keep the other two the same, I would get a different result. So let's take an example. If we use the same method, the same software, and the same person who's doing it, and if we would use, instead of 100 SAR images, we use 101 or 99, or we leave a couple of data sets out, then we already would get different results. If we use exactly the same data and exactly the same operator, the same person who is doing it, but we use either the PSI method or the SBOS method or whatever method you would like to use, you would get a different result. You get different philosophies behind it. If you would keep the data and the method the same data set, same software, but you just put another person behind the computer, that person needs to make choices on thresholds, when to accept a point and when to throw it away. And if you have a AA situation, application agnostic, you don't know what you're doing for which purpose, you will choose a value. Maybe the software has a default value, maybe not, you choose a different value, but the choice of a value will have an impact. So the very unsatisfying effect of this is that a bit different from other geodetic techniques with INSAR, it matters a lot what you're doing. And I would like to give you a couple of, and we go a little bit more back into the theory, a couple of the important things that play a role here. So it's unfortunate that I cannot get any, see if there are questions, but maybe the moderators of this lecture could pass something through if there is. Okay, let me first look at the relative nature. So one of a big scientist who was living quite close to where I'm sitting right now here in the city of Delft was Christian Huygens. And he wrote in the 17th century, 1650, he wrote whether a point is in rest or in uniform motion cannot be determined unless it is with respect to each other. And that is an amazing statement, the first one who did it. And it is very alike to Newton, who made a little bit later, 1687, he made a similar type of statement, but it was a bit different because Newton in his first law says that without any external force, a point would either be in rest or in uniform motion. So the difference between Huygens and Newton was that Newton related it to a physical mechanism, so he was adding forces to it. But Huygens purely saw it from an observational perspective. So you cannot determine whether a point is either at rest, standing still, stable, if you like, or whether it's in motion, unless it is with respect to each other. In a way, you could think now this is trivial, but the fact that something cannot be observed is very important. Now, this is important for INSAR because INSAR data are very special. They are, you have a taxonomy of Stevens. You may want to look that up in Google, for example, where we have 4 categories. So we have nominal data, ordinal data, interval data, and ratio data. Now, interval data means that we have a unit, but we don't have an absolute 0 point. And the consequence of that is that if we look at a particular INSAR result, this is a very old result from an area in the Netherlands where there's gas extraction. And what you see here are colored dots. And you see a scale with terrain motion in millimeters per year. But I don't know if this is the right scale, or maybe this is the right scale where the 0 is in the middle, or this is the right scale where the 0 is even further. I simply don't know. And this is because it is interval data. If it would be ratio data, then there would be an absolute 0 somewhere that I could define. So INSAR data is always relative to a reference point and a reference epoch, moment in time. Now, the consequence of that relative character is that if we have 3 points in our data, hypothetically, point A, B, and C in the blue in the area indicated at the top, and we look at the real motion of point A, which is like this, point B, which is stable, and point C, which is also stable. Right now, this is the real motion. This is not measured, but this is the truth. Suppose that we know what is actually happening. Now, suppose that we are using point B as our reference, then there would be no problem because point B was not moving, and point A relative to point B is subsiding after a certain moment in time. So that would be fine. However, if we would take point A as a reference, then we would postulate that point A would be stable, and as a consequence, we would see that point B and point C would go up. Now, this is the problem that we have in INSAR, and basically we cannot solve that with the data alone. So we need other information that could be either assumptions or contextual information or other observations, other techniques to solve this problem. So this is just one example to make the statement, to relate to the statement that I made in the beginning, that INSAR doesn't work. And actually it's only one, and there are many. So here's a whole bunch of them. And I don't want to go through all of them. I think this will probably be recorded, so you can pause the video and look at it. But maybe the top one is maybe the most important one. So we're measuring a phase with INSAR, an angle between 0 and 360 degrees. And 361 degrees is the same as 1 degree. And 721 degrees is the same as 361 degree is the same as 1 degree. So basically, with every observation, we have an infinite number of solutions. And this is the phase ambiguity problem. And that is very, very consequential because in essence, it means that if I don't know which one I should take, then there is just an infinite number of solutions, and then INSAR really doesn't work. Now, this is not too far-fetched. It is far-fetched in the cases that we have been looking at so far. So in the past, we had an earthquake, and we looked at the motion due to the earthquake, and we had beautiful fringes. And if the colors would vary smoothly, we would all think, okay, this makes sense, and so we can understand it. But basically what we're doing, if we're looking at the problem from that perspective, is that we're imposing our own assumptions on the problem. So because the colors look nice, because it is smooth, because this is something we expect for the situation, therefore we trust the result. But if you bring it back to its pure essence and to the mathematical problem that we're trying to solve, it's not necessarily true that if I have two pixels which are next to each other, which have almost the same phase value, that therefore there cannot be any phase jump in between them. And that holds spatially, it also holds temporally. And this is why my statement is that INSAR doesn't work. Now the question is, what can you do to make it work? Actually, you can do a lot. I will address some of these other aspects a little bit later. So the starting point, it doesn't work unless, and then the question is, okay, what do we need to make it work? Well, here's a whole list of that. So most importantly for me is that I'm not so interested in just running software on a certain set of data, making a nice picture or a nice, get some numbers and then say, okay, we're done. Because if you don't know what you're doing it for, what the purpose is, what the application is, your data is always suboptimal. So we need to know for what application you want to use it. If we can constrain the number of potential solutions, if I know that the solution has to be smooth, which in many cases is very trivial because we have mineral extraction at a great depth under the earth, so it has to be smooth. It's very possible, or most likely that it is smooth. If we know actually what we're measuring, whether the reflection comes from the roof of the house or from the street or from a tree, or if we actually know what we're measuring, then we could do more. We have problems with vegetation. If we need to have the quality of the observations in a much better way than just a fit to a model. So actually there are a whole number of things here that help us. And so within the team with which I'm working, we're trying to address several of those aspects. And so you see here some pictures from the people who are actually doing it. And I will address a couple of those things here. Okay, let's talk a little bit about the concept of optimality, because optimality is important. We would like to have results that are optimal in a certain sense. And well, going back to these typical type of products that are online available, the question that we have here is who's the end user? Who's actually using it? If there's no well-defined end user, as I said, the problem is application agnostic or AA. Now, what is quality in this context? Well, if you ask different people, they come with different answers. And well, more than 20 years ago, I was at a meeting at Esrin for ESA in Italy, and some of the ESA officials stood up in the back of the room, and he just said, "Just give me the sigma. Huh? Why do you always? You guys have such difficult stories about quality, and just give me the sigma, then I can do what I want to do." And actually, that is a great question, a great statement, but it is also one of the most difficult things to do with INSAR for many reasons. Now, if you see what kind of quality control metrics we have developed since then, that's a lot. All right, here are they. probably it's not even exclusive. So coherence, phase variance, the phase probability density function, variance covariance matrices, precision, accuracy, reliable, integrity, uncertainty, all the dilution of precision, the line of sight displacement sigma, the vertical displacement sigma. We'll get back to that later. Many different metrics. But maybe instead of going to all those metrics, we could have another perspective, which is maybe a little bit unexpected. And I would like to state this also a little bit provocatively to get my message across. So I could ask each one of you who's listening now the question, how many pages does a book have? Right? Now, that question would be probably by each one of you would be considered ridiculous, right? Because which book are you talking about, right? You can, the words here, how many pages does a book have? These are 7 words in a sentence. Sentence is great, no problem. But you cannot answer it, right? Now, if you look at INSAR and looking from space to the Earth, every square meter on planet Earth is different, right? So that means that you cannot say, well, I have a lamppost here, I have a lamppost there, so both are lampposts, and therefore I can make a statement, because the conditions will be different. And that means that similar like every book has its own number of pages, also the quality of what we're measuring is largely dependent on the object that we're studying. And the object that we're studying is planet Earth in most cases. So that means that we cannot come up with just the sigma or just the value for the based on the technology. With leveling, usually, or GNSS is already a bit more difficult, but with leveling we could more or less do that. We have calibrated instruments. We know how far the points are. Therefore, we can make a statement on the quality of leveling under the assumption that I'm measuring a well-defined point. Right? So I don't need to worry whether the point that I'm leveling to could be the second leaf of a tree or so, right? That would be very fuzzy, and then it would be probably a bad result. Now, for INSAR, that is the case. Every resolution cell, every scatterer is different on this planet. So they all will have their own different quality. And to make it even worse, probably over time, that quality will also change. So this is maybe the first unexpected perspective related to the quality of the INSAR information products. The second one that I would like to bring to your attention is that it is not a question of technology, but it's actually this quality is determined by the engineer or the operator, not by the data at all, right? So of course the data play a role, but what the person who is doing the software processing or the data processing and running the software doing, he is deciding, or she is deciding, to throw away all the points below a certain threshold in coherence or amplitude variation or whatever metric that INSAR engineer chooses to take. So basically, that means that if you put a high bar, you will probably get more points which have a high quality. If the bar goes lower, you have more points which have poorer quality. The price that you pay if you would like to have high quality is that all the points which have poorer quality are dropped out, so you will have less points. So instead of seeing the problem as something that is technical or calibration or based on the methodology, or is this software better than the other software, it is actually a choice. So the quality is a choice. If you would like to have high quality, you can get high quality because we would simply put the thresholds higher. So in principle, all scatterers or all pixels contain information, and it is the engineer who introduces the thresholds to show or hide them. So this is maybe a perspective that makes sense. So instead of asking what is the quality of the INSAR information products, we could also change it a little bit and talk about the value. Maybe that's even a better thing. Maybe what is the value of the INSAR information products? Or maybe if you even do it a little bit better, you would say, what is the value of this particular INSAR information product for this particular end user with this particular predefined problem at this particular time? Then we're getting to a question a quality-related question, that would start to make sense, right? Because the value of monitoring a bridge in Porto may be very important for the operator of that bridge, but from my perspective here in the Netherlands, I don't care that much, right? So quality in that sense, it depends on the eye of the beholder. And so the easy answer is either it's useful or it's not useful for a particular user. So the requirements are actually an identifiable end user. Somebody needs to be interested, a predefined articulated problem, and the time when this information is needed. This is the way that I look at it now. Now, sometimes people have asked me, okay, so if you give a lecture about INSAR, so what is INSAR? So just for fun, I tried to make a dictionary entry for INSAR. And this is what I would write in the dictionary. So it's a family of techniques using synthetic aperture radar interferometry to provide displacement estimates by advanced data processing, something like that. Maybe you would phrase it differently, but this is discovered it a bit, I think. Now, if you would agree with this definition, then there are consequences, and these are interesting. So if this is the right definition of what INSAR is, then the first thing is that with this technique, if it's a family of technique, we can make an infinite number of products. And this is crucial. And for those of you who are students or trying to get into the field, so I think the message is not that the technology is ready, please choose something else to study. I think it will be very important, and it will become even more important in the future, that we have people who are trained to make decisions in this data processing. It's not just software and getting a result. So we can, if we can make an infinite number of products, then you need to choose which one is optimal. And which product is optimal depends by definition on the intended application, as I try to bring across. So therefore, the intended application needs to be known beforehand. And if you would not have that, if you don't have an intended application, so you just do blind processing, it will always lead to suboptimal results. This is my proposition here. Okay, so going a little bit further into the quality assurance and control. So INSAR quality assurance and control. So these are two different things. So quality assurance is the process used to measure and assure the quality of a product, so to prevent wrong results. So in the INSAR context, you could think, for example, about phase unwrapping errors that may be in the final products, or wrong parameterization. We thought something is linear, but actually there is a sinusoidal component in there, or temperature dependent something. So you would like to prevent wrong results. And quality control, which is actually the most interesting thing here, is the process of ensuring products and services that they meet end user expectations. So if we're talking about quality control for INSAR, there has to be an end user, and that end user needs to have a question. So quality control requires a well-defined objective. It needs a product definition, and the objective is never just let's make a map and just put it on the internet, for example. The objective will always be to convey desired information to an end user, and what that information is, and that it depends on that end user. So if I conclude on this part of the lecture on the INSAR state of the art, then my main message is that it is not just the data, which are great, more and more coming. It is also not primarily the software, that one software is better than the other, or the method that you need to apply is more suitable than the other. There's no one-size-fits-all information product. That doesn't exist. It will always be suboptimal for a particular application if you don't know what you're doing it for. So for me, it is primarily the people or the experts who are able to basically first listen carefully to a problem statement, make expert judgments and decisions, gauge the value of contextual information, very important, and design an optimal procedure to estimate parameters and their quality and assist in the interpretation. That is what it is for me. So to conclude this, so I started with my statement, INSAR doesn't work. And I hope now that it was intended provocatively. and you know where it comes from. We could go from INSAR works, but well, maybe in some cases you are not so lucky there are exemptions, to the case where we say it doesn't work unless we can make some assumptions. And these assumptions rely on what are we doing it for. We need to be application aware and aligned. So AAA, that is the main message here. So with that, I've been talking for 45 minutes. I propose that we have maybe a short break I propose 10 minutes from now on. We're in different time zones, so you can check that for yourself. And unless the moderators give me some kind of signal that I can get some questions via the system, I propose that we stop here